Good morning, Richa. Today we are going to discuss about group 18 elements of the periodic table. They are also called as noble gases. So we will discuss about them one by one. Okay. So group 18 consists of elements like helium, neon, argon, krypton, xenon, radon, and newly invented element that is called as organism. These are the symbols for these one: helium, neon, argon, krypton, xenon, radon, and Og for organism. Now, occurrence, about the occurrence of these elements, we know that these elements, except radon and organism, occurs in the atmosphere. Okay, most of these gases, except these two, that is radon and organism, they occur in the atmosphere. Their atmospheric abundance in dry air is approximately 1%, by volume of which the argon is the major constituent of these 1% gases. Helium and sometimes neon are found in minerals of radioactive origins like pitchblende and monazite. The main commercial source of helium is natural gas. Helium, the main commercial source is, that is your natural gas. Xenon and radon are the rarest elements of the group. Radon is obtained by the decay product of radium 226. Radium 226, like radium 226 gives radon 222 and 86 plus 4 helium. Okay, helium 4 you can say. Now, organism, that is a new element of this one, it also synthesized by the product of collision of Californium 249 and calcium 48. That will produce here organism 294. Atomic number is 118 plus 3n. So this is how these gases occur in the atmosphere. Now next is organism. You know that is the new member of the periodic table. It has a symbol of Og and its atomic number is, that is here, 118. Its atomic mass, I have told you earlier that atomic mass, it is equal to 294. And its electronic configuration it is radon, that is your previous noble gas, 5f14, 6p10, 7f2, 7p6. This is the electronic configuration of your organism. Okay, so only very small amount of organism has been produced. Its half-life is 0.7 milliseconds. Therefore, only predictions are there about the chemistry of this one. Okay, only we have some predictions. Now, the physical properties of, we will discuss about the physical properties of group 18 elements. The physical properties, the first is electronic configuration. Electronic configuration. Electronic configuration, that is your NS2NP6, except which one? That is your helium that has 1s2 configuration. Okay, they all are inactive in nature, you know that. Okay, most of them are inactive in nature. So second thing is the reason for that one, that inactivity, that is your ionization enthalpy. So as you know that they have fully filled configuration, so they have very high ionization enthalpy. Due to this fully filled configuration, they have very high ionization enthalpy because they can't lose electrons as well as they can't accept electrons. Okay. And the third property is, that is your atomic radii. As we move down the group, atomic radii increases. You all know that why it increases. Atomic radii increases as we move down the group due to the increase in atomic number or increase in shells. That is the reason why this atomic radii increases. Fourth one is electron gain enthalpy. Fourth one is electron gain enthalpy. About this electron gain enthalpy, let me tell you how it varies in case of noble gases. So noble gases, as they have stable electronic configuration, they have no tendency to accept electrons. Okay, no tendency to accept electrons, and therefore they have large positive values of electron gain enthalpy. They have large positive values of electron gain enthalpy. Okay, and also mostly these are the general properties. They are monoatomic gases. They are monoatomic gases, colorless, odorless, and tasteless. Okay, strongly soluble in water, strongly soluble in water, and they have very low melting and boiling points. Melting and boiling points. Now, what is the reason for having low melting and boiling point? The reason is they have only type of interatomic interactions in these elements is weak dispersion forces. They have only weak dispersion forces. That's why they have very low melting and boiling point. Helium, you know that helium helium has the lowest boiling point of any known substance, 4.2 Kelvin. This is the boiling point of the helium, which is the lowest amongst all the substances, known substances. Okay, so this is why they have the reason for that one is that is the weak dispersion forces amongst them. These intronic atomic interactions, which are weak dispersion forces, due to which they have very low melting and boiling points. Now let us come to the next property, that is your chemical properties. Chemical properties. In chemical properties, you know that they are least reactive. These group 18 elements are least reactive. That's why they are also called as noble gases. Okay, they are least reactive and inertness to chemical reactivity. Okay, inertness to the chemical reactivity. That's why they are also called as noble gases. So the reason for that one is, what are the reasons for this one? The reasons are, number one is, that is your completely filled NS2-MP6 configuration, except one your helium. Helium has NS2, all other has completely filled configuration, that is your NS2-MP6. Second reason is high ionization enthalpy, and positive electron gain enthalpy. These are the two reasons why they are chemically inert. Okay, but earlier when they attempted for the formation of different compounds of these gases, they failed to do so. But in March 1962, Neil Bartlett, remember this name, that is your Neil Bartlett, this fellow of University of British Columbia, okay, observed the reaction of a noble gas. He observed that he is the first man who observed the reaction of a noble gas. So what he did, firstly he prepared a compound of, he prepared a, you can say, red compound of, formula, having formula O2 PT F6. This is the compound he obtained. Firstly, he obtained this one. Then he realized that the first ionization enthalpy of this one, O2, the first ionization enthalpy of O2, that is your molecular oxygen, was almost identical to that of your first ionization enthalpy of xenon. Okay, so their ionization enthalpy, he found that they are identical. So he made efforts to prepare same type of compound with xenon, and he was successful in preparing another red compound, that is Xe positive PTF 6 negative. He prepared this red compound from xenon. He replaced this O2 with xenon. Why he replaced this O2 with xenon? Due to their almost similar first ionization enthalpy, he replaced these two and he found a compound, that is your XePtF6, by mixing platinum F6, chloride, and xenon. He mixed these two compounds, he formed one compound, that is your xenon PtF6. Then, after the discovery of this compound, so many compounds of these xenon have been formed. After that, most of them are formed with most electronegative elements like fluorine and oxygen. The compounds of krypton are also known, but they are very rare or fewer. Only CrF2 is known. KrF2, sorry, KrF2 is known. Compounds of radon have not been isolated, but only identified. That is RnF2. It is not isolated but identified. Similarly, uh, no true compounds of argon, neon, or helium are yet known. Okay, the compounds are not yet known. Now, this is the history behind how the compounds of these noble gases are formed. Compounds of only few elements are still known to us. So how they are known to us? Next, let us discuss about the compounds of xenon fluoride. Xenon fluoride compounds. Xenon fluorine, sorry. Xenon fluorine compounds. Xenon fluorine compounds. There are compounds like HCF2, HCF4, and HCF6. They are known to us by the direct reactions of element under appropriate experimental conditions, like Xc plus F2 in the presence of at about 673 Kelvin and 1 bar, it will form HCF2 solid. Xenon is a gas, F2 is also a gas. Okay. Also, xenon with F2, when we change the reaction conditions up to 873 Kelvin and 7 bar pressure, it will form HCF4 solid, 2F2. Then Hc gas plus 3F2 gas, it will form at about 573 Kelvin and 60 to 70 bar pressure, it will form HCF6 solid. Okay, here the ratio is xenon in excess. Here the ratio is 1:5 ratio, and here in this case the ratio is 1:20 ratio. If we mix these two compounds and these ratios and at these conditions, they will be the compounds. These are the compounds which are formed after this. HCF6 can also be prepared by the reaction of HCF4 with O2F2. It will form HCF6 plus O2. The hydrolysis reactions of these compounds are very important. So hydrolysis of HCF2 with H2O, it will form He plus HF plus O2, the balance reaction, 2H2, 2, and 2H2O and 2HF, 4HF. Similarly, the reactions of XPF2 with PF5, it forms XEF positive and PF6 negative. Okay, that is called as fluoroanions. These are also called as fluoroanions. Okay. Next, similarly, HCF4 with SBF5 forms XEF3 positive and SBF6 negative. Next, let us suppose second part, xenon oxygen compounds. Xenon oxygen compounds. Let us discuss about these compounds also. They are formed by the hydrolysis of HCF4 upon hydrolysis. Okay, it forms 4Xe plus 2HCO3 plus 24HF plus CO2. These are the compounds that xenon oxygen compound which is formed by this reaction. Similarly, if we hydrolyze HCF6, H2O, it forms HCO3 plus HF. So balancing the equation will give us HCF6 plus 3H2O gives HCO3 plus 6HF. Partial hydrolysis, partial hydrolysis of these compounds of HCF6 gives oxyfluorides, oxyfluorides like XeOF4 or XeOF, XeO2F2. For example, HCF6 on hydrolysis, partial hydrolysis forms XeOF4 plus 2HF, and from this HCF6 plus 2H2O forms XeO2F2 plus 4HF. So these are the compounds, that is oxygen, non-oxygen compounds, and how they are formed. Okay. The next is about the structure of these compounds. For example, let us discuss about the HCF2. I have told you that how we can draw the structure of this one. Xc, in simple method, Xc has how many valence electrons? They have 8 valence electrons. Okay, 8 valence electrons. Now, if they have 8 valence electrons, how many are bonded here? 2 bond pairs are there. 2 bond pairs are there. So how many non-bonded are there? 6 non-bonded electrons are there. 6 non-bonded electrons are there. Okay, 6 means there are 3 pairs, 3 non-bonded pairs, and we know that these 3 non-bonded pairs, they are called as lone pairs. So total of 3 plus 2, 5 hybridized orbitals are there, and you know that the shape for 5 is like this, diagonal bipyramidal. But here, if 5 bonded are there, then this is the shape. But here in this case, we have 2 bonded and 3 lone pairs. So the shape will be xenon, 2 bonded. You know that chlorine should be far away from each other due to their small size and high electronegativity, and 3 lone pairs are there. So this is your linear shape. Similarly, let us discuss about HCF4. Valence electron, how many are there? 8. Okay. Bonded are equal to 4. Non-bonded, out of 8, 4 are bonded, so 4 are non-bonded. So that means lone pairs. How many lone pairs? 2 lone pairs are there. Okay, if 2 lone pairs are there, total 4 plus 2, 6 hybridization. It means 6 for regular. This is the shape of 6. But if 6 are bonded, then this is the shape. But we have here 4 bonded and 2 lone pairs. So the shape will be like this: xenon, chlorine, and 2 lone pairs are there far away from. Okay. So this is your sphere planar shape. So with the help of this one, you can also draw the shape of, let us suppose, XeOF4. XeOF4. So here Xe again 8. Now here bonded are, how many bonded are there? You can see from here, bonded, how many bond electrons are there? 4 with F and 2 electrons with O. 4 with F and 2 electrons. You know the oxygen always forms 2 bonds. So 2 bonds are there with oxygen. So total 6 bonded are there. And non-bonded are 2. Non-bonded 2 electrons. 2 electrons means how many lone pairs? 1 lone pair is there. 1 lone pair is there. So the structure as the shape is 2 and 1 lone pair is there. Okay, so here 4 and 1, 5 elements are there and 6. For 6, the shape should be, if it is not a your irregular geometry, or you can say without this one. For 6, this is the shape for bonded. All are bonded. But we have here xenon. One is with oxygen and other one are with the chlorine, and one lone pair is there. So the shape is here, pyramidal. Here, pyramidal. Okay, so also you can try to draw the shapes of other compounds of this one, that the compounds of xenon, and similarly, as we have drawn all these compounds, you can draw the other compounds also. So this is about the compounds of this one. Last one is uses of group 18 elements. What are the different uses of group 18 elements? So helium is a non-inflammable and light gas. Helium, non-inflammable and light gas, used in filling balloons for meteorological observations. It is also used in gas-cooled nuclear reactors. Okay, gas-cooled nuclear reactors. Liquid helium, cryogenic agent. Okay, for various experiments at low temperature. Powerful superconducting magnet. Okay, it is also powerful superconducting magnets. Okay, which form an essential part of modern NMR spectroscopy and magnetic resonance. It is used in NMR and magnetic resonance imaging. Okay, it is also used in that diluent for oxygen in modern diving apparatus because of its low solubility in blood. It is used by the divers. Okay, so it is used in diving apparatus. It is used in diving apparatus due to its low solubility in blood. This question was also there in your second chapter, solubility, why they carry this one by diluting helium, why they add helium to their cylinders. So this is the reason why they dilute oxygen with this one. So the reason is low solubility of this one in blood. Neon is used in discharge tubes. Okay, and fluorescent bulbs. Argon is used to provide an inert atmosphere in high temperature metallurgical process, arc welding of metals or alloys, and for filling electric bulbs. Argon, filling electric bulbs.